Hello, good day. Today I'm going to be actually telling you how to design steel. Steel is a bit different from concrete. It is homogeneous, that means it is made of the same material, same strength throughout. Okay, let's start. You will be just going through my notes that I use regularly when we are doing steel design. This steel design is done mainly in two parts. Under the limit state design, that is what we are going to be doing, we have what is called plastic design, and we have what is called elastic design. There is a difference between the two. Okay, I'm sure if you are used to concrete, you are aware of two things. The first thing is that you design for bending moment and for shear force. Then at the very end, you design for deflection. But when it comes to steel now, you do a lot more checks. Okay, I'll just come back to this in a moment. Okay, you do 5 things as opposed to 3 in concrete. You design for bending moment, you design for shear, you design for deflection. Then on top of that, you've got what is called local buckling and what is called torsional buckling. These are key because the last one, let me rush to say something about that. Lateral torsional buckling, under this it says the load at which the beam buckles can be less than that. Okay, sorry about that. The load at which the beam buckles can be much less than that, causing the full moment capacity to develop, which means that it can fail due to torsional buckling before it reaches its moment capacity. I'm sure if you've gone to school, you've learned about this. This might be coming as a shock to you, but this is exactly what happens. Okay, so the thing that causes local buckling is what is called slenderness or classification of sections. Okay? So to do your classification, you use this table here. Okay, let me show you how it's done. The B is actually this part from half of the flange. Okay. If you divide it by T, the big T is the thickness of the flange, you come up with a number that is less than 9 epsilon. Epsilon is actually 275 divided by Py, which is the strength of the steel. Okay, so the steel that I normally use is actually 275, which gives it 1. Okay, so if you just divide these two, the number that you come up with, if it's a 7, it will be 7 epsilon, which is less than 9 epsilon. It is plastic. But when it is less than 10 but greater than 9, it is a compact section. Okay, it is a compact. Then is a semi-compact is something less than 15. That is for the flange. Now for the web, you divide the B, the D, which is the gap or the size, actually the height of the flange or of the web, divided by its thickness. If it is less than 80, it is considered to be a plastic member. Okay, for plastic design, you only use class 1. Now for these other classes, they are a bit different, but they are called elastic. They are used for elastic design. Okay, as you can see here, for class 1 plastic cross section, this can develop a plastic hinge which with sufficient rotation capability to permit redistribution of moments in the structure. Okay, so if it's something like a portal frame, and then you're going to do what is called moment redistribution, it is important that you stick to class 1. Okay, I think I'm giving you too much information. I'll then go in depth as we go. Okay, This is just an introduction to the design of beams. I told you in short that we are looking mainly at 5 things when we are dealing with steel. We are looking at the moment, the shear, the deflection, the torsional buckling, which we found out it is more important than the moment capacity, and then finally we are looking at what is called local buckling. Okay, local buckling occurs in section in class 2, 3 and 4 because of the thickness. Mainly it's because of the thickness of the section. These unlike popular beliefs, the plastic section is actually the one with the thicker gauge. Okay, thank you. We'll get into it as we go. Thank you for your time. Please subscribe, like and share.